Okay, now it is recording. Now you can start. What about the students? Scott students?
Scott?
Yeah, hi.
Where are all the students you invited?
There are actually 3 seminars at least going on at this moment,
Oh,
unfortunately.
okay.
So I'm
Okay,
sorry
very
about that.
good.
There's a
Very-
gravitational wave talk going on, for example.
Well,
here
we
comes-
got one more.
I know. Rakesh. Hello, Rakesh. Hello. Why is he muted?
Yeah, he has the mute button on. He has to turn on his microphone. Here, let's chat to him. Well, you go for it. You know him.
Hello, Rakesh. You have to unmute yourselves.
Yeah, if his microphone's off, then he knows that we are. Tell you what, if he doesn't want to talk, he can just type in. I can go ahead without his microphone. We can, yeah. There we go.
Okay. You can start.
I'm not able to unmute. Well, should I continue then?
Yeah.
All right, let me just alt tab here. I'm going to first alt tab to, and then we'll tab to this, and then I will share the screen. Okay. All right, can everyone see that on my screen? The black hole is asymptotic darkness?
Yes, we can see it.
Yeah. Yes.
All right. So this is my seminar on my own independent research on black holes, and really a big rabbit hole that I was not expecting to find, but did. And I want to open this up with, oh, hang on, I want to make sure I'm on my slides here. Yeah. My first disclosure, full disclosure, I am not a physicist. I am not a mathematician. My highest level of mathematics was I took calculus in college. So I am not an authority on anything I'm going to be talking about. That's actually a fact. I'm consulting the authorities. I consider everyone in this meeting and anyone really interested in delving into this, you're who I'm trying to talk to. I'm not trying to really become anything more than someone researching a project. So I'm not a physicist or a mathematician. I hold a master's in cellular and molecular biology, and I developed the theory as an extension of my fiction writing. I'm writing a story. It's about dark matter, and I researched dark matter. I was very unsatisfied with the evidence I found. So I began this project, and it's led me several places, but let's say it led me to this seminar. So the premise, this is the premise upon which I can base the entire theory and proposal going forward. A massive particle approaching a black hole will never cross the event horizon nor enter the black hole interior. If I were to put one thing in the science books, it would be this. It's not math. It's not really related to advancing theory. It's about changing one thing, in my opinion, and this is it. So let me just, I don't know, elaborate on this. We'll start with the basics, and you'll have to forgive this presentation. This presentation is a little bit older. It was designed with the intent to be able to share with anybody who had even a mild interest or understanding in relativity as I've learned it. So we're going to imagine a light bulb, and this light bulb flicks on, and it startles this bee. So this bee's on top of the light bulb, the light flicks on, and the bee gets startled. And this is a very fast-moving bee. Now it's sitting on the light bulb, and it flies away. We can call the light the origin and use radial coordinates, but changing coordinates doesn't change anything that's happening. So let's just imagine our origin, and the bee flies away. And here's time moving forward as the light pulse expands in space. It does not matter how fast the bee flies, it can never pass the pulse of light, which expands spherically from the origin, because particles cannot exceed the speed of light. Depicted in this image is time interpreted as 3 frames or slices. These slices can be connected by imagining connecting the upper and lower edges of the circles with lines that follow the path of light through every slice of time. So as you can see, what I've constructed here is a fundamental light cone, light expanding through time. So you can draw it like this. Not only can this light cone be drawn, but we can also draw an inverse light cone to time before the light comes on. A coordinate system can be applied to the light cone to keep track of our B, which is moving at a very fast and at a constant velocity. Now, one might ask, hey, why do you include the light cone before the light turns on? Well, it's not just that things can't go faster than the speed of light. It's that anything ahead of the light turning on can be said, this is part of the cause of that light turning on. Nothing from outside that light cone in the past can affect the light at all. So whatever turned on the light, it's inside that light cone. That's all I wanted to mention to that. Now you'll suppose the bee is observed by someone moving at a very high speed. So imagine the light and the bee are in a house and you're going by on a train close to the speed of light. Now the coordinates for this observer would be different than those of the light bulb. You can see how much closer the bee is to the edge of the light cone. A transformation can be applied, which conserves the speed of light. This Lorentz transformation can be applied, which conserves the speed of light. This Lorentz transformation does not affect any of the physics. It only solves for observations at relativistic speeds. Note that the bee approaches the edge of the light cone, but cannot reach it. Again, there's no frame of reference where this bee is going to exceed the speed of light. So we've got a very, very, very reliable system here as to how particles move through space-time slower than light while also conserving the speed of light. Now, I write this all to drive home the concept that anything within this section of the light cone cannot escape from within. This is very key. Everything in my theory is going to come back to this light cone and how there can only be particles inside that section. It has to be in there. Now, the light feels no forces as it moves through space, and thus its path must be its straightest possible path. The straightest path is called a geodesic. In the case of light, the path is known as a null geodesic. Geodesics are coordinate independents, so coordinate transformations can change the way they are depicted, but cannot change the geodesics themselves. So I like to use the analogy of a field. If you can imagine a field of grass, you've got your options. You can draw a baseball field on it. You can draw a soccer field on it. And you can play those two different sports on those two different coordinate systems, if you will. But you don't change anything about the field. You're just adjusting the coordinates to play the game you want to play. That's how I like to think about it. It's a lot more technical in general relativity. I'm well aware of that. But I think it's a good analogy to move things along. The curve of null geodesics increases as the curvature of space-time increases, which increases in proximity to the gravitating body. The closer the light gets, the more it curves. So, of course, we can imagine a gravitating body, and light close to the gravitating body is curved greatly, and light moving further away from the gravitating body will not be as curved. Very simple to understand. As space-time is curved, these gravitational fields slow time down as it would an object was approaching the speed of light. However, since the space-time is not flat, the speed of light, this is something I wish I'd edited out. The speed of light actually slows. There's debate there. I've heard some people say, well, no, the speed of light doesn't change at all. Some people say, well, it's accelerating, so the observer will say the speed of light is this over here and that over there, but it's really the same. Again, this is something that I really need to learn much better as to whether the speed of light is changing in accelerated reference frames. But let's just go with what I've written here. The speed of light actually slows the moving object. This will cause the previously discussed light cones to close. So let's ignore the idea that the speed of light is changing and just embrace the geometric reality that as you approach a gravitating body, your light cones will close. Now, a key argument. The law of general covariance states that the form of the physics will not change under coordinate transformations. The light cone is light moving through space-time, and thus it must be coordinate transformation independent. The light cone is the form of the physics. As you acknowledge the law of general covariance, you then must acknowledge that the changes in the light cones are physical. They're mechanical. They're real. Here's my key criticism of the current theory. Modern physics is not taking exact solutions for the Einstein field equations as exact solutions. We use the Schwarzschild example. Here I have this is sourced from a YouTube video. We have outer solutions and inner solutions. Why do we have outer solutions and inner solutions when the Schwarzschild is an exact solution? We have an outer solution and an inner solution, I submit, because there is a preconceived notion of the path of particles into black holes. And in order to have that, we need inverted equations within the black hole from the equations that are outside of the black hole. My recommendation, of course, is we don't need the inner solution. We use the outer solution all the way down. And my proposal is that if you do that, you'll come to the following conclusions. So that's my key criticism. Now, we'll move to a black hole and, oh, sorry. One
Sorry,
moment,
Ben,
one moment.
correct
I
me
gotta
if
hit
I'm
okay
wrong.
here. Sorry?
Correct me if I'm wrong, but this RT are the Schwarzschild coordinates, right?
Yeah,
So-
Schwarzschild coordinates, yes.
So what it all says is that the validity of the coordinate is no longer true at beyond the event horizon, right?
I wouldn't say
So-
it's not valid. Here, let me continue. I'll answer questions at the end. Let me just
Okay,
continue
yeah,
at the
sure,
end here.
sure.
Now, this brings us to black holes. The current theory of a black hole is that there is an event horizon where time stops, and thus light can no longer be emitted. So anyone observing would not witness a mass falling all the way inside. Now, you'd see the mass, it would appear to get closer to the event horizon, but what actually is happening is it's going into the black hole and into the central singularity. The mass would appear to stop releasing any signal at the event horizon. However, what is actually happening is that the mass passes through the event horizon and into the singularity. The singularity is the ultra-dense core of the black hole, which every time I say this, I don't get much pushback. And that's dangerous for me because I'm going out to prove that all that's wrong. So let's move down here. At the event horizon, the light cone closes so much that the two null geodesics are on top of each other. Remember that any particle inside a light cone cannot escape from inside of it. But for the event horizon, there is no inside of a light cone of the event horizon. Thus, there can be no massive particles at the event horizon. There is literally no space nor time for them. Physicists have proposed to solve this problem with coordinate transformations. However, you must remember that geodesics are coordinate independent. Beyond that, there are no coordinate transformations in existence that can put space between two lines that are on top of one another. The event horizon is closed. All particles exist outside. And I think well, let's move on. The light cones of a black hole close at the event horizon. That is the form of the physics. So why does a black hole appear the way it does? What is the singularity? What is the event horizon? These questions are quite rudimentary. Here is the metric of an uncharged, unspinning black hole. This is the spherically symmetrical Schwarzschild metric, which I'm sure you recognize. If we calculate above the event horizon, we have I don't want to call it a trace, we just have a coordinate system that can be read as a negative value and 3 positive values. This can also be a positive value and 3 negative values, depending on how you want to equate them. But the focus here is I have a negative and the positive in the 1, 1, and 2, 2 coordinates of the matrix. But if we go below the horizon, we get an inversion. And that's just basically by the numbers. The numbers just simply insist that if you're going to insert a coordinate below the event horizon, then the values you will return will be positive, negative, positive, positive. Thus, between 1, 1, 2, 2, we have an inversion. So note there is an inversion between above and below the event horizon. Since the metric is a spherical metric, we only need to invert a sphere. So a sphere, invert it, you get a pseudosphere. There it is, a pseudosphere. The pseudosphere has negative curvature. If it were gravitational, its gravity would be repulsive. Thus, if a black hole's interior is pseudospherical, it would be free of particles because the surface is repulsive. So you can imagine particles trying to get in, but the negative curvature of a pseudospherical geometry would evacuate them to beyond the event horizon, which I've already stated, there's not even any particles there. But that's not as easy as it gets. Still, if we look, understanding the fact that the event horizon itself is a singularity, a simple conclusion presents itself. From the polar view, a black hole and a pseudosphere are identical. If I look down the barrel of a pseudosphere and I look at the cross-section of a black hole, they're exactly the same. There's a perimeter singularity for the pseudosphere. There's a perimeter singularity for the black hole, known as the event horizon. And there's a central singularity in both. So it looks as though you simply invert a sphere. There you go. You get a black hole. Now, wait a second. What would an inverted black hole look like? I guess it'd look like a white hole. And things get very interesting now because from the outside, it'll look like a black hole. And from the inside, it kind of looks like a white hole. And you kind of run into the inability to describe what's going on depending on how you look at it. But what I wish to propose is what's going to happen is nothing's going inside there. The geometry is just not right for anything going inside this shape. So let's move on. Now there's a pseudospherical problem. The coordinate singularity of a pseudosphere is at the equator, okay? So when you have a pseudosphere, you have two extensions and a singularity along the equator. If the black hole is a pseudospherical, then there cannot be one surface below the event horizon. There must be two surfaces within the black hole. But we only see one, don't we? The Gabriel's horn is like the surface expected, but without a second half, it cannot be called a pseudosphere. So here we have a Gabriel's horn. It's I guess I want to call it a hyperbolic surface that goes off to infinity over here. But if this was analogous to a pseudosphere, there'd be another half. It wouldn't just go in one direction, it'd go in both directions. So I have to find a way to put another half onto my Gabriel's horn and get a pseudosphere. Well, that takes math. And you wouldn't believe it, but it turns out there's a simple trick to get there. Now, we'll use the Einstein-Rosen transformation of the Schwarzschild coordinates, a very simple means of finding the second half of the pseudosphere. U squared equals r minus 2m, which can also be written as u squared minus r plus 2m equals 0. This, of course, is a polynomial. Furthermore, the black hole interior is entirely made up of complex solutions. If I go into the event horizon according to these numbers, I'm going to get negative values for u squared. So I'm going to have complex solutions. Question for the audience. Can you think where I'm going with this? I've got complex solutions in a polynomial. All right, I'll just move on. Complex conjugate root theorem. The solutions for the complex numbers of the Einstein-Rosen are expressed as both a plus bi and a minus bi in accordance with complex conjugate root theorem. Thus, the surface must be mirrored across the I-axis. In treating the complex numbers as coordinates in higher dimensional space, we complete both sides and find ourselves a hyperpseudosphere. So the equator, which is normally a circle in a three-dimensional pseudosphere, becomes a full sphere in three-dimensional space going into higher space. That's the proposal. I'm a little upset about this because I know it's not calculus. It's just polynomials and complex conjugate root theorem. Very, very, very basic. So I would like to have a version of this theory which is more grounded in calculus, but this is all I have to work with for now, I'm afraid. In any event, mathematically, it appears to get the job done. Now, here's the infalling mass problem. We know things are falling into the black hole, but if they're not going inside the event horizon, well, what's going on with them? Mass is falling towards the black hole, never falling inside the black hole, so what is going on? The conclusion drawn by myself was dubbed space-time boiling in an independent discovery. I was sitting there thinking about mass falling into a black hole, but not going inside of it. And I developed this concept that I called space-time boiling. That was an independent discovery of an already discovered phenomenon. The actual term is known as asymptotic darkness, and we won't be calling it space-time boiling. We'll be calling it asymptotic darkness. Let me give a quick demonstration of how I imagined it. We're going to imagine this is a block of mass, all right? If the interior of a black hole is repulsive, then there's nowhere for the falling matter to go. So we have a block of mass, and a black hole is opened up inside, and it's surrounded by this ultra-dense mass that cannot collapse inward. Imagine a block of matter so dense that it can become a black hole, and one does form inside of it. The gravity around this black hole forces more matter into it. Without anywhere to go, this infalling matter becomes more dense. So all around this black hole, new black holes are forming. Around those black holes, new black holes form. And around those black holes, new black holes form. And this process continues indefinitely. And what I was shocked to find out when I consulted someone who clarified that my independent discovery was already named asymptotic darkness was that this was actually discovered by analyzing quantum scattering. So quantum scattering reached this conclusion, and I came the other way with it from general relativity, which I think is interesting. Now, this is known as asymptotic darkness. Black holes are not just one giant event horizon around a singularity. It is a teeming morass of matter and inverted space-time, all competing for existence through the overpowering force of gravity. Now, asymptotic darkness is stable. The behavior of asymptotic darkness appears to be sustainable indefinitely outside of entropy. And entropy of asymptotic darkness is a profound and a very enormous topic in which I'm very interested, but I have none of the qualifications to pursue the entropy of asymptotic darkness, because there would be particle entropy in asymptotic darkness, and there's also the question of Hawking radiation. So of these two definite forms of entropy, I don't have any answers. I'm sorry about that. Now, we can thus imagine an entire universe of asymptotic darkness. Let's do a thought experiment where we collapse the entire universe into a black hole, and then we take the universe itself and we collapse that onto that asymptotic darkness. We've now got a universe entirely of asymptotic darkness. Now, if we suppose that dark energy were to inflate a universe of asymptotic darkness, then when the dark energy overcomes gravity, the universe would be forced to open up new space-time. And you can imagine the energy released when asymptotic darkness is torn apart. The only suitable mental model would be a Big Bang. So we have a universe of stable asymptotic darkness inflated into a Big Bang by dark energy. My proposal. Now, this comes back to using the Einstein-Rosen coordinates. If the Einstein-Rosen coordinates used to establish the pseudospherical geometry, they also predict Einstein-Rosen bridges. When I started this research, I didn't care about black holes. I didn't. I was wondering about dark matter. Why did galaxies stick together in clusters when they didn't have enough mass? What I learned is that generally dark matter halos form around galaxies, and galaxies themselves form around black holes. So black hole, galaxy, dark matter halo. Nice layer, nice layering of the different objects. Now, these black holes make up an insignificant amount of mass in the galaxy, but the whole galaxy and dark matter halo forms around it. How? I mean, we call them supermassive black holes, but I believe I'm going to guess here. It's 40 million solar masses is the weight of Sagittarius A star. But can I get a thumbs up on that, Scott? 40 million solar masses?
I'll just say yes.
Okay. Well, we'll imagine 40 million. Let's estimate that 40 million solar masses. It's not out of the ballpark. In any event, I'm pretty sure it's less than 100 million solar masses. We're talking about a galaxy of 200 billion stars orbiting a 40 million solar mass black hole. That, in terms of orbital mathematics, that makes no sense. So here's a proposal. I propose that Einstein-Rosen bridges, wormholes, can form between two distant patches of asymptotic darkness, black holes. These patches would be joined by a bridge as if there were a gravitational string that would put tension on the universe. And if you have these 2 points of tension in the universe being drawn together by this string, you're going to curve the space-time of the universe in which you exist. You won't know where the curve is coming from because you can't see it. It's higher dimensional. But this is my proposal for the dark matter curvature. There is some evidence pointing to this conclusion, as black holes, which share the same cluster, also share common spin at distances too great to directly influence one another. So if you have a number of galaxies in a cluster and you study their spins, it appears, or it would seem, that all of the black holes are influencing the spin of the other, and they are aligning, and there's no explanation for it in the universe, so I'm suggesting a higher universal solution. If the string of the Einstein-Rosen bridge connection is being twisted, so if I twist one end of the string, and that's heading down the Einstein-Rosen bridge, and on the other end, the string will also spin along with it. And again, a proposal. Now, I'm hopeful that this hypothesis is not wrong. Then we'll have an explanation to the state of the universe before the Big Bang, a model for black holes, and a solution to unite physics through string theory. That's, I'm told that this is close to, I think it's, is it ER equals ERB? I'm sorry, I don't have it off the top of my head. I should have studied that. But in any event, if the behavior that I'm describing is real, and it is analogous and can be described as string theory, I think it's a potential to unite quantum mechanics and gravity. I'm really hopeful for that. There's also one other additional thing that I did not include in the slides. Here, I'll wait on that. The other thing that I did not include in the slides is the information paradox. The information paradox right now, very difficult thing with black hole physics. I submit that my theory doesn't have an information paradox. The information paradox requires information to cross the event horizon. And again, I'm saying that doesn't happen at all. So thus, you have no problem with the information paradox. And as I described earlier, you don't have any problem with the Big Bang singularity either, because there isn't a Big Bang singularity. There's just asymptotic darkness in the proto-universe. So it's easy to imagine if you know what you're thinking about. And it kind of breaks away from the concerns of the information paradox and the pre-Big Bang universe. So let's move on. Now, so here's my conclusion. This is a 2-page conclusion. Particles cannot and do not cross the event horizon into the black hole interior. Black hole interior is hyper-pseudospherical according to the Einstein-Rosen coordinates. Black holes exist entirely as asymptotic darkness. The universe existed as asymptotic darkness prior to the Big Bang. Dark matter and intergalactic black hole spin alignments may be induced by Einstein-Rosen bridges, and if the theory produces a gravitational string theory, then it can unite gravitation with quantum mechanics. And thank you for your time. I will end with my slogan, all things through sacrifice, sacrifice through all things. Thank you for your time.
Okay. I don't know what is the quotation about sacrifice.
That's just me. If you want, I can. Here, how do I get back to my camera? Never mind. I'll just leave it as that. The quotation about sacrifice was my attempt to build up a morality for myself, and I looked at the laws of thermodynamics, and the laws of thermodynamics are, let's see here, that you cannot create or destroy energy, that that entropy will always increase within a closed system, and that you cannot reach absolute zero and reach a state of zero entropy. Now, how I interpreted that was kind of like the saying, if you want to make an omelet, you got to break an egg. I think that's how everything actually works. As we go through our lives, since we cannot create or destroy energy, we only have what's in this universe already to work with. So if I want to make a house, I got to cut down a tree. I have to sacrifice the tree to make the house. All things through sacrifice. Now, as I make my house, I saw it up. I create a lot of sawdust, and that sawdust isn't useful to anyone. So I've wasted energy to produce something that only added entropy to the system. Thus, sacrifice occurs through all things. All things
Okay.
through sacrifice, sacrifice through all things, the laws of
Okay.
thermodynamics.
Okay. Krishna wanted to ask something. Can he remember the question?
Yeah, I was
Hang
just
on, I'm going to check.
wondering about the charts that you're using. So basically, you're using the Schwarzschild chart, and you have an outer and an inner solution because the validity of the Schwarzschild solution.
Oh, whoa, hang on. I'm screwed up. I've screwed up. Okay, I want to get back to here. I want to go back to, hang on. I hate to share my screen. Who knows what I've got on here? Oh, this is not good. Presentation, where's the button? Oh, it's right here, yeah. Okay, which slide would you like me to stop to?
The one that you were showing the inner and the outer solution to the black hole in terms of the
there we
R
are,
and T.
right here.
By the way, you're not sharing your screen for some.
Oh, shike, you're right. Alt tab. Oh, well, good. If I'm not sharing my screen, then I didn't show anything worrisome.
This is the bottom,
Hold.
at the bottom of your
I
screen.
got it. I got it. Bottom, share screen. There.
Yeah, so the reason you have an inner and an outer solution is because of the validity of the Schwarzschild coordinates, right? But if you had
Say
chosen
again?
to,
The what of the Schwarzschild coordinates?
so the Schwarzschild coordinates are only valid as it is, the solution that you wrote down in terms of metrics in the couple of slides ahead. They are
Mhm.
valid only up to the event horizon. And then you have to look for the change in the R and T that you have shown already in the, when you are looking at the solution beyond the event horizon. But you could have as well worked with the solution which is valid throughout the space-time, right? That is like the Eddington-Finkelstein coordinates, for example, or the
No,
Kruskal.
I'm aware of the Eddington-Finkelstein coordinates, and the Eddington-Finkelstein coordinates. Yes, you can get not
So the
only.
idea is that don't attach.
If I may,
Yeah.
the Eddington-Finkelstein coordinates are of course based upon the tortoise coordinates, and the tortoise coordinates, as I understand them, they have an open light cone which does not change with altitude either, or from the interior or the exterior of the black hole. So, and they're very convenient that way because you can imagine a world line passing down to the black hole. The problem with the Eddington-Finkelstein coordinates is they don't coordinate for the event horizon. There's no solution for the Eddington-Finkelstein at the event horizon. You get natural log of 0. It's undefined. It doesn't work for the event horizon.
Yeah,
So
so I was
you're
going.
presenting. So hang on. You're presenting to me an entire coordinate system that is lacking the very thing I'm trying to talk about. So it doesn't really help me in
I
my
was
theory.
going
I don't think it helps
a
the theory in
step
general.
beyond. So you exponentiate that and you get the Kruskal extension, right? The Kruskal coordinates.
Yes.
So
Oh yeah, Kruskal.
those coordinates are the one that is valid throughout the space-time, right?
And yet Kruskal coordinates do exactly what I'm showing here. They also invert the coordinate system below the event horizon. How about, yes, I know that the Schwarzschild, the interior solution, according to, look, the transformation I use is the Einstein-Rosen. What does the Einstein-Rosen give you for the interior? Complex numbers. How does that help us? But if you do, and if you accept the complex numbers, I submit to you that those complex numbers can be treated as a dimension that you can't use in a 4D space-time metric. So my transformation, I don't need the Kruskal because the Kruskal is going to do the exact same thing. It's going to have exterior coordinates that are one way, and it's going to have interior coordinates that are inverted. I don't need this swapping of inversion between the top and bottom of a black hole. In fact, I think that's part of what's driven us to this point, is this inability to understand that you can't flip around what's going on inside the black hole so you can draw world lines that don't make any sense. A world line going from outside the black hole into the singularity, again, I'm going to submit, is nonsense, because it's going through what's been called anti-de Sitter space, hyperbolic space, hyper pseudospherical space.
Can I ask a question? Can I ask, what is U squared? What is U?
Sorry?
What is
What are you?
U in your equations?
I
You have
can't.
U
I'm sorry.
squared minus R minus 2m equal to 0.
Oh, yeah. Here, hang on.
What is
Let
that
me
U?
get to the
What
let
is
me get
that
to
U?
there. There it is. U squared equals R minus 2m. This is the Einstein-Rosen coordinates. These are the Einstein-Rosen transformation for the Schwarzschild metric.
Why do you, well, I am confused. Inside the black horizon, the problem is that there is no time like kilometer. So time evolution is, so the problem becomes already an issue of how to define time evolution inside the horizon.
Oh yeah, but I can define the event horizon very simply. I define it as a null light-like surface. Now here's the thing. There are other situations where people say, oh, look, you're passing through a null surface, so therefore you can pass through a black hole's event horizon. Let's say I'm in a rocket and I have a friend with me and we're accelerating towards the speed of light. Now below us will form a Rindler horizon. As we're accelerating, we're getting away from the light behind us, so we get a horizon, right? I throw my friend off the rocket ship, okay? And he falls towards that Rindler horizon, correct? And that's a null surface. From my perspective, as I'm accelerating, that Rindler horizon is a null surface. And my friend passes right through that null surface. I don't see him do that. I see his image at the top of that Rindler horizon for as long as I'm accelerating. If I accelerate forever, then there will be some form of his after image left on that horizon for absolutely ever, even though he's fallen through it. Perfectly valid. Here's the thing. The instant I throw my friend off of my spaceship, we're in different coordinate systems. I'm still in my accelerated reference frames. He is in an inertial frame. And in an inertial frame, you're not going to have a Rindler horizon, obviously. So this disagreement is because we're in two different reference frames. When it comes to gravitation, we're all in the same boat, if you will, generally. When we see a gravitating black hole, that's a physical object. And if that physical object has a null space event horizon around it, then we're all going to have to agree that's a null space event horizon because it's objective. By definition, if it's made by an object, it is objective. This isn't a disagreement between reference frames. It's a physical thing.
Actually, I
Well, I
have
think
a
there's just an enormous amount of confusion about coordinate systems that's going on here, and it's driving most of this talk.
I
Right
really
at the
don't think
beginning,
it's
you
a
said the
confusion about
particle
coordinate
doesn't fall into
systems.
the black hole. That's an incorrect statement. It's a function of just sticking to the Schwarzschild coordinate system, which is known to fail at the event horizon.
Good.
So you
So
have
let's
to
do the
use a different
transformation.
coordinate system, whether it be Kruskal or whether you patch together different solutions. You know,
There's
there is
my
no
answer.
physical problem with the event
Yeah.
horizon. The particle will just pass straight through it.
No, you don't. It's a physical null surface. There's absolutely no space to do that. It's not time-like. It's light-like. By definition, it has to be light-like. Why? Because it's nothing but light cones collapsed onto one another. By definition, that has to be just a light-like surface. And I can't have a massive particle on a light-like surface that is objectively real, because that's the same as saying I can accelerate to the speed of light. I know I can't do that. So I know I can't get to this event horizon for the exact same reason.
I have an observational question that maybe is related to what Simon's saying. Have you thought about how stars would collapse to form the black holes? Because from what I can understand, you're taking the black holes as a thing given.
Yeah.
How do you form them? If what you're saying is true,
All right.
form.
All right. Okay, I can go in two different directions with that. The first direction is the traditional one. I've got a hypermassive star, supernova, and the supernova happens in such a way that it doesn't produce multiple pulsars, or it doesn't distribute the mass in anything but one solid object. That's too massive. It's gonna collapse under its own gravity. It's gonna get too big. It's gonna form a black hole. So I can get a black hole that way. Now,
Can we
there's
stick
another
with that? Can we stick with that one for a minute?
Sure.
How would the coordinate system describe that process?
Same as that, same as a Schwarzschild. Well, I have to assume it's not spinning, right? I'm sorry, I gotta take away spin and charge. I'm sorry I don't have the math for
Sure,
that.
no, it's okay. I'm just saying when it's collapsing, it'll reach
Yeah,
a
none
point
of this
where-
depends on spin and charge.
Yes.
Let's go
Okay,
with
yeah,
what
none of this
Scott's saying.
depends on spin and charge. I'm just imagining if I do have a collapsing physical star, it's gonna have angular momentum as it collapses, but let's ignore all that. And look, let's say I have a collapsing star and it doesn't turn into a black hole. What do I get? A neutron star. And a neutron star is just going to be a bunch of particles smushed so close together that they're pushed right up to the edge of the exclusion principle, I think it's called. No problem there. Now let's just squish it a little bit more, and the exclusion principle maybe still works, but the scattering becomes so intense that you start opening up black holes. Asymptotic darkness. So it's just a simple system. It's like you can imagine, look, you just make this soup. You make this black hole soup, and it does this. That's just what it does. So however you want to form it, at the end of the day, it's going to look like this.
Well, black holes do form astrophysically, and they do correspond to particles passing through event horizons, if you want, or forming.
I do not. No. Particles passing through event horizons is not necessary. As long as I have mass and enough of it and dense enough, I get asymptotic darkness.
So you don't believe in accretion disks or anything like that?
No, accretion, obviously, but that's obviously the exterior.
But what's heating the stuff up if it's not falling into the
There's
black
no
hole?
heat. Well, the heat, I called it space-time boiling, but that wasn't meant to be an indication of heat. I would like to have more in-depth and intimate discussions about the heat of asymptotic darkness, but that goes back to the entropy problem, which I haven't got the first idea about. That's part of the reason I'm coming here, is I'd like to convince somebody enough to say, okay, let's say we get asymptotic darkness. What's the entropy? What's the heat? What's the information? Start knocking those things down, because that's well above my pay grade of 0.
I'm okay. Anyway,
Wait, I want to. If I completed with the stellar, I want to go back to a black hole forming. I was very satisfied with the discoveries of the James Webb Space Telescope. You know why? Because they found black holes that were too big to have been formed after the Big Bang. They were too big to be formed after the Big Bang. Thus, the conclusion must be they existed before the Big Bang. And that is a part of the theory. If we have a universe of asymptotic darkness and I expand it with dark energy until it bursts, then I'm going to get leftover black holes from that. The black holes at the cores of galaxy, I submit, are primordial. They came from the asymptotic darkness of the pre-universe, and now they're what's left over.
the problem is you are not using quantum mechanics at all, quantum theory at
No,
all.
I'm not. No,
You are using
No, I'm not.
visual pictures.
sorry.
This is for me, it's a big problem because I don't think visual pictures explain nature. So, for example, Riddler wedge, that is nowadays completely understood from the quantum point of view. Okay? There is no problem. You can write even whatever you want to write.
Yeah.
You can write it down. Yeah. So,
But I have no problem with quantum mechanics because the asymptotic darkness that I'm describing emerges from asymptotic darkness.
but you
I've
did
only
not
needed
use.
to I've needed to submit it though from general relativity because it presents
No.
itself.
No, you have to also present. Well, it's up to you. Okay.
Look, this is part of the reason that I'm making these proposals is I need a certain level of research beyond my ability. And believe me, if I could publish or make any statement about quantum asymptotic darkness, I'd be making it right now.
But you have to start, sorry, you have to start from a quantum theory of black holes outside the horizon. That already
Sorry?
is problematic. So that's already problematic. So let alone the further visual pictures, it gets really complicated.
It does. It does. But
Anyway,
as I've demonstrated, if you just follow the general relativity as I understand it, it's going to lead back to the same conclusion.
okay.
And if I call it space-time boiling, then I can say, okay, I did it all myself and it's all general relativity. I can't do that because it was discovered before I did. I've got to stick with how it was discovered. And it was discovered by quantum mechanics that I don't understand.
Okay. Maybe are there further questions? If not, I will. Are there people? Who is Drew Colosimo? Who is Drew Colosimo?
Hi,
Drew,
I was invited by
You are
Scott.
Drew Colosimo.
are you in
Yes.
Colorado?
No, I'm in Syracuse. I'm from
Hey,
Col-
cool. But I'm glad you're representing the Rockies.
Thanks.
Okay. All right. So are there questions?
I don't have any. I'm an undergrad. I didn't understand most of this.
Okay.
Well, I apologize. I really wanted to try to make it as forward as I could, but I'm really having a hard time with people hashing out coordinate transformations to me. I understand that that's what's been delivered to the student body and the academia and everybody. And I understand that I'm saying, no, you got to stop doing that. And I'm a person of very, very, like next to zero qualifications to do that. But in a way, that's kind of how it has to be, because only somebody from outside is going to yell at the inside and say, you're doing it wrong. At the same time, of course, everybody inside is going to say, no, we're doing it right. So I'm in a tug of war with the entire academia, and I'm all on myself, pulling one rope while everybody else has got their hand on it on the other side. But in my defense, I have presented a coordinate transformation. It is the Einstein-Rosen. And whether or not the Schwarzschild is functional below the event horizon is kind of irrelevant if I've got a working coordinate transformation. I submit that I do.
Okay. If there are, I wish you good luck, Ben. Let's see what
I'd like
happens.
to thank everyone for coming here today. I've waited a long time to
Okay.
deliver this seminar, and it's been it's been an honor. And anyone who wants to continue this discussion, I'm more than anxious, more than ready. Let me put it this way. I can imagine a lot of astrophysicists being kept up at night wondering about this stuff. I don't get kept up at night by wondering this stuff at all. I sleep like a baby until I realize this is in my head and I've got to get it out there. That's what keeps me up at night. How the hell am I going to get people talking about this? That's it.
Okay.
Thank
All
you
right,
again all.
thanks.
Ciao,
I
ciao.
have- Thanks,